Who's a hockey fan here? There's a few of you that are hockey fans, some of you that play hockey. This is the logo of the San Jose Sharks. The San Jose Sharks right now are 6-0. They have outscored their opponents, I believe it's 25-10. So they're doing pretty well right now. This is a train. What do the San Jose Sharks and this train that are chugging down the track, what do they have in common? Wow, that's a good answer. And a quick answer, too. They both have momentum. Now, it's a different kind of momentum, right? When you talk about a hockey team that's difficult to beat, and that's really what we're talking about, right? It's hard to beat them. They're 6-0. They've scored 25 goals, and they've only let in 10 goals. They're hard to beat. They've got a lot of momentum, but it's more of a psychological momentum. There's no real physical reason why you can't beat them. It's more psychological than anything else, as opposed to this train that has physical momentum. Well, what fundamentally is the same about both of these things? Okay, what is momentum? What does it boil down to? This train, as it moves down the tracks at whatever speed, whether it's 60 kilometers per hour or 6 kilometers per hour, is difficult to stop. This hockey team, if they're 6-0 and they've outscored their opponents 25-10, is difficult to stop. Momentum is how hard it is to stop something. The more momentum something has, the harder it is to stop. Trains have lots of momentum. How come? Because they got not a lot of weight, although they do, but more fundamentally, they have a lot of mass. What else determines how much momentum a train has? Because really, of course, that's what we're talking about in Physics 30, right, is the physical momentum. Trains have a lot of mass. They have a lot of momentum because of that. What else gives a train a lot of momentum, possibly? Their force and acceleration, not so much force and acceleration, but you're on the right track. Bryson? The velocity. Momentum is dependent upon two things. It's dependent upon mass and velocity. The heavier something is, the harder it is to stop. The faster something's moving, the harder it is to stop. So we're going to define momentum in just that way, the product of an object's mass and velocity. But we're going to think of it as how hard it is to stop an object. So the real definition, product of mass and velocity. But the way we think of it and the way that we understand it, the way that makes more sense to us than a definition of product of mass and velocity, is how hard it is to stop something. There's a term from Physics 20 that sounds different than the term that we just defined, momentum, but the definition of it is pretty similar. Anybody remember what that term is? It starts with an I. Inertia. Momentum and inertia are very close to being the same thing, but they're not quite the same thing. Momentum is how hard it is to stop something, product of mass and velocity. Anybody want to tell me what inertia means from Physics 20? The tendency of an object to not necessarily continue moving. Tendency of an object to continue at the same velocity. Yeah, the tendency of an object to resist a change in motion. So isn't that the same thing as momentum, how hard it is to stop something? If something's moving and it's got a lot of inertia, it's hard to stop, right? It's got a lot of inertia. It's got a lot of momentum. Is there ever a situation where you could have a lot of inertia but not very much momentum? The tendency of an object to resist a change in motion. That includes you right now. You're sitting in your desks. Your bodies resist a change in motion. You have inertia, but you're not moving. Inertia is dependent upon one thing, whereas momentum is dependent upon two things. What's the one thing that inertia is dependent upon? Not velocity. Somebody said it? The mass, yeah. Inertia is dependent upon mass. You have inertia because you have mass. That train has inertia because the train has mass. Train also has momentum because it's got mass and velocity. Is it possible for the train to have both momentum and inertia? Yes. Is it possible for the train to have one or the other, momentum or inertia? No, the answer is yes. It is. If it's going to have one, but not the other, which one is it going to have, momentum or inertia? Inertia, because an object at rest can have inertia, but it can't have momentum, right? As long as you got mass, you get both. As long as you have mass, you have inertia. If you have velocity as well, then you've got not only inertia, but you've got momentum as well. Is it ever possible to have neither momentum or inertia? Not if you got mass. It's possible to have no momentum if an object is at rest, but it's not possible to have inertia, to have no inertia, because the object is going to have mass. I'm going to show you a picture here of two trains. One train is moving down the tracks, one train is in the train station. Let's assume the mass of both of these trains is the same. How does the inertia of diagram 1 compare to the inertia of diagram 2? They're equal. If they both have the same mass, they both have the same inertia, despite the fact that the first one is moving and the second one isn't moving. How does the momentum of diagram 1 compare to the momentum of diagram 2? Diagram 2 has no momentum, diagram 1 does, because the object has mass and it's moving. So what do we say inertia was again? It's the tendency of an object to maintain its current state of motion as opposed to how hard it is to stop something. Momentum is dependent upon mass and velocity, whereas inertia is dependent only upon mass, not the velocity. Is it possible, two diagrams you see up on the board here right now, is it possible to ever do anything to train number 2 to give it more momentum than train number 1? Increase its velocity, make it go faster, sure. Maybe you stop train number 1. Maybe you make train number 2 go really, really fast. Is it possible to do anything to train number 2 to give it more inertia than train number 1? Not unless you make it heavier, right? If we keep the train the way it is, then no. If you get a bunch of people on board, then it makes it heavier and it gives it more inertia than train number 1. Does that make sense, guys? The difference between momentum and inertia here? It's a small thing, but it's an important thing. Momentum is a vector. It means it's directionally dependent. If the velocity is in a certain direction, the momentum is in a certain direction as well. Let's think about that, right? If it's dependent upon mass and velocity, a scalar and a vector, then what do we end up getting? A vector. Scalar and a vector come together to give us a vector. Mass and velocity give us momentum, a vector. The equation, there's really only one equation for momentum, and it's a pretty straightforward one. Momentum P, that's a lowercase p, by the way. If I said capital P, what would I probably mean by that? What symbol is given by a capital P? Power, right. It's a capital P with no half arrow over it. This is a lowercase p with a half arrow over it. So it means it's momentum, which is a vector. It's equal to, it's dependent upon the product of mass and velocity. That's its definition. So the equation is going to be mass times velocity. Anybody want to take a stab at the units for momentum, despite the fact that you've never seen them before or heard them before? What are the units for mass? Kilograms. What are the units for velocity? So the units for momentum would be kilograms times meters per second. If you're in kilometers per hour for speed, what do you got to do? You got to convert to meters per second, yeah. How do we convert, let's say, 100 kilometers per hour to meters per second? Now, there's the way that I taught my physics 20s, which is convert 100 kilometers to meters. It's 100,000 meters. And then we convert seconds to hours, multiply by 1,000, divide by 3,600. We end up getting 27.777 meters per second. What's the shortcut? Divide by 3.6. I didn't teach that to my physics 20s. Kilometers per hour to meters per second is always divided by 3.6. Meters per second to kilometers per hour is always multiplied by 3.6. Good. Let's do an example. Okay, our sample problem is from your textbook that you don't actually have yet, but it's okay because you have it up on the board in front of you right now. Example 9.1, page 451. Please feel free, by the way, when we're doing these these example problems on the board, to not write down the problem. Just reference it in your notes. Just put example 9.1, page 451, and that way you know where to find it when you need to go back and study for your tests, or when you're doing your homework and you need a little bit of help. But please do write out the solution. If you photocopy or if you download the notes from my website for tomorrow, you will see exactly what you see on the board right now. Okay, that's fine. You don't need to recopy it. But you do need to copy out the solution that I'm about to give you. When I see this question, the first thing that goes through my mind is, okay, we're looking for momentum. I only really have one equation in this unit, P is equal to m times v. Let's write down some givens. I got to write down some givens. Now, if you have the question written down in front of you already, you've got a couple of options for your givens. You can circle them and just make some notes, or you can write them out separately, like we always did in Physics 20. The velocity is 3.0 meters per second. We'll define east as positive, by the way. Velocity is 3.0 meters per second. What's the mass here? What mass do I want to use here, Nick? Good, 250 kilograms. This is not a hard problem, but that is one place that's easy to make a silly little mistake. Right? You put a mass of 180, you're wrong. If it's a multiple choice question, I guarantee you one of the options will have used a mass of 180. We're looking for the momentum here. Now, if you've got it written down in front of you already and you don't want to go to the bother of writing out the givens like I have right there, then just circle things. We get to this and we say, oh, the velocity is 3.0. Write that down, velocity. Mass is 180 and 70. Let's just write down mass is 250 here. We're looking for the momentum. We're looking for P. So if you want to just make notes in the question, I can live with that. But the givens should be written down in one form or another, whether it's with the question circled or underlined or highlighted, or whether it's separately on the side like I have here in blue. Now let's solve the question. P is equal to m times v. The mass is 250 kilograms. The velocity is 3.0 meters per second. We multiply them together, lightning fast calculations here. We get 750, or 7.5 times 10 to the 2 kilograms meters per second. 2 digits there, right? It's a positive answer. We define positive as east, so that means the momentum is to the east. The velocity vector is already drawn for me. Looks like this. The momentum vector, well, if the velocity is to the right, which way is the momentum? It's always got to be in the same direction as the velocity. So the momentum vector would look just like this. Both of them drawn to the right. Let's take a look at these two practice problems now. We'll give you probably about 5 minutes to sit at your desks and do these. Got a question? Raise your hand. I'll walk around and you can get some help from me or get some clarification from me. Make sure you write down your givens. Make sure you write down your equations. Make sure you do all of that stuff. Make sure you have your units in your final answer, the right number of significant figures. Again, if you have any trouble with any of that stuff, then just put up your hand and ask me. All right, if we're having no trouble with these questions, let's move on to another example question here. It says, this one's not in our books, so we're going to have to copy this question out, unfortunately. This one says, a 1.5 kilogram object falls from a height of 14 meters. What's the momentum of the object as it hits the ground? We've got an object that's a mass of 1.5 kilograms. Right? Let's write that down as m. It falls from a height of 14 meters. So we're going to say let's say hi. The initial height is 14 meters. We want to find the momentum as it hits the ground. We're not only looking for momentum, P, we're looking specifically for PF, the final momentum as it hits the ground. Now, somebody this morning said to me, oh, its final momentum as it hits the ground is 0. I said, no, it's not. Why did you say that? He said, well, because it's not moving when it hits the ground. Oh, good point. It's not moving. Once an object hits the ground, it's not moving, right? If I laid you down on the ground in front of the classroom there, I stood up on top of a desk. This is what I did with a student this morning. Took a hole puncher and threatened to drop it on him. He's a little scared of that because it would hurt, right? The hole puncher would hurt if it hits him in the head. Why? Because it's not moving when it hits him? No, because it is moving when it hits him. When this object hits the ground, it's moving. Otherwise, it wouldn't hurt. After it hits the ground, it's not moving. But as it hits the ground, when it hits the ground, it's moving. So if it's moving, it's got a momentum when it hits the ground. Let's find that momentum when it hits the ground. PF is equal to m times VF, the mass times the final velocity. Well, the mass is given to me in the question. It's 1.50 kilograms. But the final velocity isn't given to me in the question. And it's not 0. Does anybody want to take a stab at how I might find the final velocity in this question in order to ultimately find the final momentum? Go ahead. Sorry, I'm not even sure who I was pointing to there. I was going to point to Nick, and then all of a sudden at the last second I saw a couple hands up at the back here. What do you say? Times what by 9.81 squared? times something by 9.81 meters per second squared. You're on the right track. We can't just simply multiply some random number by 9.81, but it does have to do with gravity. Go ahead, Nick. Like this? Okay. So VF squared is equal to VI squared plus 2AD. Assuming it's dropped, then its initial velocity will be 0, and then the final speed will be the square root of 2 times neg 9.81 times, what's the displacement here? If its initial height is 14 and it hits the ground 14 meters below, what's its displacement? Negative 14 meters, right? Let's calculate that. Let's get the value for the final velocity there, final speed. We're going to say it's the square root of 2 times neg 9.81 times neg 14. What do we get there? 16.5734 meters per second. What have I just found again? No, I haven't found the final velocity. What have I just found? You're close. I found the final speed. This equation doesn't have a vector sign over it, does it? It's the final speed. If the final speed is 16.5734, what's the final velocity? Negative 16.5734, because it's moving downwards. So let's plug that number in for the final velocity, negative 16.5734. And when we multiply those two numbers together, let's see what we get here. 24.9 or negative 24.9 kilograms meters per second. Final answer comes out to be a negative value. What does that tell us about the final momentum? It's negative, yeah, but which way is it acting? Downward. If the velocity is downward, then the momentum should be downward, of course. All right, let's take a look at this one. I'm going to ask you guys to do this one yourselves for about 3 minutes, and then we'll take a look at it as a class before I assign your homework for the night, okay? Some of you have had a chance to either finish this or come pretty close to finishing it. Some of you are still struggling a little bit with it. Let's read through the question. Let's point out some things that we need to be able to find, that we need to be able to pick out of it as we're reading this question on a test or an exam. It says, batter hits a fly ball. The .130 kilogram baseball moves at a rate of 20 meters per second at a point where it's 5 meters above the ground. I'm just going to skim through the information to start off, and then I'm going to read the question. I'm going to see what seems to be really important, and then I'm going to go back and read the question a little bit more carefully, or the information a little bit more carefully. It says, what's the magnitude of the momentum of the baseball the instant before it strikes the ground? So we want to find momentum. We want to find momentum, and we want to find it the instant before it strikes the ground. Let's go back to the question, the information here. We've got a mass of this baseball of 0.130 kilograms, and it's moving at 20 meters per second at a point where it's 5 meters above the ground. So when the height is 5 meters above the ground. What strikes you about what I have circled in the information and what I have circled down there in the question. Something jumps out at me. The fact that I've got information given to me for when this object is 5 meters above the ground, but I want to find information for when the object hits the ground. Does that make sense? So I'm dealing with two different things here. I've got givens for one place, and I want to find something for another place. Something's got to give there. It's probably going to come in the question. In the question, I'm probably going to find information about when it's on the ground. And then I'm going to use that to solve for the momentum as it strikes the ground. P is equal to m times v. The final momentum is equal to the mass times the final velocity, the velocity as it hits the ground. The mass of the baseball is 0.130 kilograms. What's the velocity of the baseball the instant before it strikes the ground? Not when it's 5 meters above the ground, but the instant before it strikes the ground. How do I find v? Let's do it the same way as we did in the last question. Let's say vf squared is equal to vi squared plus 2ad. Vf is equal to the square root of vi squared. Vi this time is not 0, it's 20. Plus 2 times neg 9.81 times neg 5.00. Because in the end, that's how far the ball falls. 5.00 meters downwards. That's going to give me the final speed. Let's do this on the calculator here just to make sure that we can get it. Let's say square root, let's use some brackets here, 20 squared plus, let's use some more brackets. Pay attention to the brackets that I'm using here so you don't make a mistake on that, okay? It's 2 times neg 9.81 times neg 5, end bracket. Then we're going to end the bracket again to finish it off. We end up getting a final speed of 22.318 meters per second. If that's the final speed, then the final velocity will be negative 22.318 meters per second. We're going to multiply that by 0.130. And we end up getting a final answer of negative 2.90 kilograms meters per second. So the answer for this would be D. Notice in the question they say, what's the magnitude of the momentum? In other words, we're not looking for the direction. We're just only looking for the magnitude of it, how big it is. This question is the same questions we just had, isn't it? It's the exact same questions we just had. But it looks slightly different because this time it's a baseball. Don't get lost in that. Okay? Don't get caught off by the fact that it's a baseball being thrown or whatever. Okay? It's a question where we've got an object at a certain height. We want to find the momentum as it hits the ground. We've got to get the velocity as it hits the ground from its initial height. Exactly the same as the example problem that we had. Okay? Good question. That's a good question. Nick just asked, what if the baseball is hit at a height of 5 meters, right here, at 20 meters per second, and it goes up as opposed to down? Well, eventually, of course, we know it's going to come down, right? It doesn't matter what path it takes to get down. It doesn't matter whether it goes straight down or whether it goes up and then back down or over and then down. It doesn't matter. As long as we have the initial velocity, the initial speed of 20 meters per second, and the height, it doesn't matter what path it takes because speed, initial and final, is a scalar. Acceleration is neg 9.81, and the displacement is not what path it took, but its final position minus its initial position. So its displacement would be -5. Vertically, its displacement will be -5. So again, it doesn't matter what path it takes to get there. What matters is that it ends up on the ground. If it gets hit up in the air at 20 meters per second, or it gets hit straight down at 20 meters per second, its speed when it hits the ground will be exactly the same. Well, what happens if, let's look at it this way. Let's say it went up in the air. Let's say you threw it down like this at 20 meters per second. Okay, it's going to be moving at a certain speed when it hits the ground, right? if it goes up like this at 20 meters per second, well, it should be going faster or slow, right? But when it goes up, just hold on for a second there, guys. When it comes back down, at this point, it's going to be moving at 20 meters per second again. So it's going to take longer to get to the ground, but it's still going to be moving at the same speed when it hits the ground. The path taken is irrelevant there. That make sense? Okay, your homework for tonight, don't take off before you find out your homework. Although, you could just follow me on Twitter and find out what the homework is tonight, right? It's worksheet number 1. Okay, worksheet number 1. Pleased to have that done for tomorrow. 27 homework checks last semester, Physics 30, period 3. The odds of you guys getting a homework check tomorrow are, I wouldn't say 100, but it's pretty good. All right, have a good night, everyone. We'll see you tomorrow.